Yeah, that'll still happen.
I might not be last week.
I mean, I would still like for you to try the equilibrium lab. So,
I mean,
sorry.
I've done like half of it, but once I got to the negative number, I was like, do you want me to turn it in partial?
Yeah, I mean, you get partial points. Sorry. I'm just trying to pull up everything still. All right, let's get started, I guess. Apologies, that hour, losing the hour really destroyed me, to be honest. So I'm super behind on your grading. So, I don't even have my mic on my face. All right. So a couple of issues that people have let me know about. So apparently the equilibrium lab is still not working. Uh, so apparently they're still getting negative values. So I'm going to just ask that you calculate with negative equilibrium values. So I know that doesn't make sense. I will try to look at the data, but again, I've spent like way too much time last week troubleshooting this lab, hence why I'm like super behind on your grading. And then to find that it still doesn't work, I mean, I really don't know because I've been teaching the same class with the same labs for 5 years, and this lab has never been this pesky where like you can't get a correct number. So I don't know. Like I said, I'll try to look through the data myself and play with it, but we really are just like running out of time. So just please move forward and do your best with this negative calculation, and we'll just again have to deal with it. If you have lab makeups, I need to know ASAP, like yesterday. Right, so as you've seen, these last few labs, especially the two kinetics labs and then apparently the equilibrium lab, are super sensitive. So they need time to make the solutions for those. I don't know if people are missing other things, but please let me know ASAP. And we can still do lab makeups next week. So that is also an option if we can't get them in this week. So it's probably going to be too hard to do a lab makeup today unless, yeah, I mean, I'm not sure what lab it would be because like we said, those solutions are super finicky. Uh, and then we do have our lab finals, so that is happening this week. So during your lab period, and you'll have checkout with that as well. You will be doing an in-person lab thing. It should go better than the equilibrium lab, I'll say that much, but you will have to do something in lab by yourself. So I think it'll be okay. It'll be a good opportunity. And then, I mean, I can't believe we're at the end of the quarter here. So yeah, like I was saying, turn everything in. I apologize for being super far behind on grading. I just have an online load as well that I know you guys don't see, but it keeps me occupied with tons of grading on there too. So I'm just super behind, but trying to catch up. For this week's quiz, we'll probably just have to do like a trade and grade because I'm still behind on your last week's quiz. Again, that hour our loss was gone, so I'm super behind. And then if you're missing stuff, let me know. Again, we can fix it. I have like no names, so that's why I like really need to get papers back so then people can figure out who the no names are and all sorts of missing things. All right, so we need to finish up last week. And so we want to do the 5% approximation. And like I said, that's going to carry us over to our acid-base chapter, which we do have the last homework for. And okay, so now we're saying we have this 5% approximation. So when our equilibrium constant is very small, and I think this will become a little bit more apparent in practice. So when we have our acid constant, usually we say like 10 to the power of 3 difference. And we'll calculate this out, but once you start seeing those order of magnitude differences in like Ka values, then we say that it's usually safe to do our 5% approximation. And so all that's saying is, right, your equilibrium value is pretty close to your initial value since that change, again, is less than 5%. And so saying, right, it'll be essentially the same. And so if our approximate value of x is less than 5% of our initial concentration, then we can use this approximation. All right, so now let's practice that. So we'll see. And right away, this is kind of your hint that you have a pretty small Kc equilibrium value. So okay, that's kind of telling you that maybe your change in x will be kind of small. And so let's look at this. So we have the decomposition of hydrogen disulfide. So 2 equivalents goes into 2 of H2, 1 of S2. And we're looking at our Kc. So it says we initially have 0.0125 moles of hydrogen sulfide, and to find our equilibrium concentrations. So see if you can start that. And again, you can make your 5% assumption, so see how that goes. All right, how are we looking so far? So, right, we just started with our rice table, which, like I mentioned, we'll keep seeing once we do acids and bases today. So, initial concentrations, and again, this is one of those where we only have reactants, so we know we're going in the forward direction, even though, right, it's probably going to be a small amount in the forward direction, as you can guess by this Kc value. So minus 2x plus 2x plus x, right, for our appropriate coefficients. Just making sure we're all on the same page, then change, then our equilibrium. All right, so now let's start plugging in for our equilibrium expression. And first I'll write our generic, so H2 squared times S2 over H2S squared. And it's now plugging in things. So now that's 2x squared times x over 0.0125 minus 2x squared. And so now this is where we can make an approximation. So we can set this, of course, equal to the Kc that we had set up here. So 1.67 times 10 to the negative 7. And then let's just make our 5% assumption. So we can always go back, right? So that's kind of the caveat of this trick is like if we're wrong in this assumption and we check it, then we do have to go back, right? And then solve it by the full quadratic. But otherwise, let's make our assumption. So assume less than 5%. So then that makes our bottom a little easier. And so I didn't finish distributing out the top. So 2x squared gives us 4x squared and then times x. So 4x cubed, right? Over, so now this is 0.0125 is equal to 1.67 times 10 to the negative 7. And then from, squared, sorry, I almost forgot to square that. And so from here, right, that makes the algebra a lot simpler. Sorry, let me get my calculator fired up. So 0.0125 squared, and then multiply 1.67 times this to get rid of it. And so divided by 4, and then take the cube root, so to the power of 1/3. And so this should be our answer for x then. So 1.87, we'll round it, times 10 to the negative 4th. And then this is when we want to double check. So now check our 5% approximation, right? Were we correct in making that assumption? And like I said, you can always make the assumption and then check it, right? And make sure that that was a good assumption. So divided by our original concentration, so 0.0125. So times 100. So, right, 1%. So we are within that approximation, right? So the approximation was good, so less than 5%. So 1 point, yeah, question?
What happened to the minus 2x on the denominator? When you scroll?
Here?
Yeah.
Yeah, so that's what we were saying, right? So assume 5%. So we said that this change, the minus 2x, was negligible.
Okay. So does it account for every like
So it's only we can make the 5% approximation, right? So if we can't make the 5% approximation, or, so you don't have to do this, right? Like that's the other thing, is this gives you technically a slightly inaccurate answer. You like don't have to do it. So like you're more than welcome to solve it with the full quadratic. Like you never have to use the approximation, right? You're not required to do that. That's just something that makes obviously your life a lot easier. But you can go ahead and mathematically solve it, right, by whatever way you want.
Get the same answer.
Yeah, basically, right? So they'll be off with a little bit of rounding. I'd probably solve this one with a computer calculator. Not ChatGPT though. ChatGPT is like does not do quadratic functions correctly. Like Wolfram Alpha will, but not ChatGPT. But yeah, so you could still plug this into like a computational program and get X that way. Like I said, you'll get a small discrepancy. But otherwise, right, if you're solving it in class by hand, I would recommend taking this 5% approximation. And then we checked it, confirmed that it was only about 1.49% change. So yes, it was valid to take our approximation. So again, that's why we were able to get rid of that minus 2x, since it was such a small change, right, compared to the 0.0125 molarity. And so then we can go back and solve for our equilibrium concentrations. And so now we can take the 0.0125 and then subtract, right, our 1.87, I'll round it to, times 10 to the negative fourth. So then there's our equilibrium concentration. Did I do 2x? No, I did that wrong, so sorry. So minus an additional equivalent. So there's our equilibrium value for hydrogen sulfide. So 0.0121. And then our other ones were, so 2x and x. So H2. So about 3.74 times 10 to the negative 4. And then let me know if you have questions or got different things.
How do I know that the hydrogen sulfide is a minus 2x? For the ice,
Yeah, so it goes back to we only have reactants, right?
yeah,
So then what direction must we go in?
different reactants. I think it should be like
Yeah, so then if it's going in the forward direction, that's our only option. There's two equivalents, so that's why we do minus 2x, right? And then same thing, so then the products are formed in plus 2x and x, right? Again, for their coefficients.
just to balance out the reaction.
Yeah, because that's the rate, right, that they're going to be forming at. And then the last one, so about 1.87 times 10 to the negative fourth. Those are all molarities. Questions about that? And then the last bit of this chapter was this Le Chatelier's principle, which I think the lab kind of did a good job of going over. I don't want to spend too much time on it because I want to get to our acids and bases, but I do like the graphical representation. I think that's kind of useful. So we're looking at this reaction, and again, we're always looking at these dimerization reactions. So now we have the dimer versus the monomer. And so first we see they're in equilibrium. Again, right in our mind, we know that the reaction is going back and forth, but overall concentration isn't changing. And then we saw this with our equilibrium lab, so that part at least did work well with part C, stressing it out. And so notice how you artificially perturb your equilibrium by adding in this case, we added a bunch of product. And then the product, notice how it gets consumed, goes back to a new equilibrium level. And then, of course, right, we make new N2O4 as well. And then reestablish equilibrium, right? K is the same, but different values of equilibrium. And so that's what the color, again, stressor was doing. And so I think people figured it out. Let's do this little practice. Well, actually, I'll skip down to what I was thinking about. So you had to kind of figure out for your little blood reaction if it was endothermic or exothermic. And so kind of the trick was that you treat heat as either a reactant or a product. And so, right, if it's a product, if it's an exothermic reaction and you add heat, then it shifts away, right, from the added heat. And so what did you find with your little test tube? So did it go lighter or darker? When you put it... Yeah, so it should have gone lighter, right? And you kind of had to marinate it for a while was my suggestion. So put it in there, and then it should have gotten lighter. And then so based off of that observation and kind of looking at this, right, so seeing the equilibrium will shift away from the added heat. So then based off of this is the blood red reaction exothermic or endothermic? Yeah. Yeah, so then it'd be exothermic. So then, right, I'll just write this out. Plus SCN gives us our iron SCN. And then, yeah, so we could put plus heat. And so, right, sometimes we have the triangle that symbolizes heat, or I'll write out heat. But that's another way to think about Le Chatelier's principle. And then if the opposite were true, so if it had been endothermic, right, you would have been put it in the heat and it should have gotten like super, super dark red, but again, that did not happen. All right, let's try this practice problem. So look at our equilibrium expression, and of course, pay attention, right, to our states of matter. We said that piles of solid don't affect our equilibrium. All right, so what happens when we add CO2? So it causes the reaction to shift. So left, so good, right? Again, so we want to shift away from the added, in this case, product, so it would make more solid. And then if we add calcium carbonate, what effect does adding calcium carbonate have? So good. So no effect, right? It's a solid, so it's just a big pile there. So good. No effect on our equilibrium.
So meaning that gaseous and aqueous are the only things that have an
Correct.
Okay.
Yeah, and so that means, right, like a neat liquid reagent will not affect it either. And I think your homework was really good for kind of practicing that. And yeah, so chat agrees, so our answer choice ends up being B there. And then, so I don't want to, like I said, I want to move on to chapter 20. So we add a gas. Again, we see that that does change the equilibrium, like we were just saying. Um, Obviously, volume would affect a gas, so then we'd want to just calculate, right, our new volume and pressure of our gases. But of course, that would not change solutions. And then with Le Chatelier's principles, so one way to kind of affect it is to write, you can decrease the volume or increase the pressure, or vice versa. So if your volume decreases, then your equilibrium will shift to fewer gas molecules, right, to attempt to get rid of that pressure, or again, vice versa, right? You can increase the volume, and then equilibrium will want to favor more gases. So we saw that with volume. Again, the Haber-Bosch process, so that's one way to control it. So they do run this reaction at high pressure, and you are going from 4 to 2 moles of gas. So that's a good way to drive it forward. All right, let's do this one real quick. So what is the effect of decreasing the volume of this reaction? What if you increase the volume or add an inert gas? So what happens if we decrease our volume here? Which way does it shift? Left, right, no effect? Yep, so it should be left, right? So there's 3 moles of gas versus 0. So shift left towards reactants. And then if we increase the volume, will now be the opposite, right? So increase volume. So now that's going to be shift to the right, create more gas. And then adding an inert gas at constant volume. It doesn't really have an effect since it's not part of our kind of equilibrium expression. So yeah, no effect there. All right, that's pretty good. Let's see what else. Yeah, since it's not part of the reaction, so it's our inert gas, so not part of our expression. So yeah, I think we know our endothermic, exothermic. Again, I would just write a little heat symbol to help us. So endothermic, right, heat is essentially a reactant. Exothermic heat is a product. And then I think it's pretty easy to figure out our relative shifts. All right, so let me fire up our chapter 20 notes, and I probably need to fix some links. I noticed that like those links expire really quickly. I don't know, I may have to like try to redo all of them. I don't know why they're set to expire like quickly, so I'll try to fix that. So yeah, if you need notes for the exam, just like send me an email. I might have to refresh the link because like I said, I was trying to go through them and I was having a few issues, but I don't know why they should expire, but there could be some weird RCC SharePoint setting. All right, so now we're looking at acids and bases. And I feel like we touched upon acids and bases like a small amount first quarter. We've seen a few reactions, but let's kind of go over everything. And so acids, right, they have a sour taste. I don't know if people are obsessed with sour candy now that they make. And so a lot of the sour candy is a lot of different like acids, like citric acid is used a lot and all sorts of other like fruit-based acids. I wouldn't recommend tasting HCl or anything like that, obviously. But acetic acid, right, vinegar, so that's also kind of got that sour taste to it. We've seen this over time, right, that they can dissolve many metals, especially like nitric acid. We've seen HCl, right, that works to dissolve magnesium pretty nicely. Of course, it can neutralize bases and vice versa. We've seen that. And we do have our citric acid spill kit. If we use our simple paper, we can change our blue litmus paper to red. Usually we just like the universal paper. That's always a lot easier to look at. And then, so we'll get into this in the chapter as we go on, but we have our strong acids like hydrochloric. Then we also have our weak acids like our organic acids like this acetic acid. And well, let's point out at least. So here's the structure part of an organic base acid. So this carboxylic acid group, so we'll see this again. And then just common acids. So hydrochloric is used in like metal cleaning, some food preparation, a lot of refining, again, from dissolving metals. It's also your stomach acid. Sulfuric is, again, used in like fertilizer, explosives, manufacturing, batteries, electroplating. Nitric acid is also used, again, in fertilizer manufacture. Acetic, again, food preservation, pickling. Citric acid, so again, candy making is a big one. So usually it's like cheaper to buy citric acid. That's like for candy making, you can buy it bulk. And then, right, citric acid is found, of course, in your fruits, so lemons, limes. And then again, there's obviously a bunch of other alternative fruit acids that are used in lots of candy. So like glass frosting and etching. So HF, this is like kind of one of those dangerous chemicals. So you would have to have, I forget what the calcium compound is, but right, there's some sort of calcium compound that you have on hand if you do use HF, because I think I mentioned this before. If you get HF on you, you might not necessarily feel it, but then the problem is it goes to your bones and dissolves your bones, and then the problem is that calcium could re-solidify somewhere in your bloodstream and cause, right, like a stroke or something. So be careful with HF. That's personally on my I don't want to work with it list. And then phosphoric acid, again, is used a lot. Biological buffers is where you see it, or also beverage preservation, like your sodas have a little bit of phosphoric acid in them. And then, so we were looking at these organic acids. This is the one I was thinking of, but I couldn't think of the name. So malic acid is another one that's used in foods a lot. And so again, they have this carboxylic acid group. And so we can start to see, and this slowly gets into OCHEM as well. But let's start getting into, well, why is this acidic? And so this is called our acidic proton here. So this is the one that's going to be leaving. And so we want to see, well, why is it favorable for this to leave? And so this can pop off. And so notice, well, let's first write out the structure. So hydrogen leaves, we're left with a negative charge on this oxygen. But now we can write our resonance structure. So notice, right, I switched arrows. So now I want to write resonance. And then let's look at our electron action. So we always want to start action at the electrons. I'm going to now make a double bond here. Well, we can't have 5 bonds to carbon, so now this goes back up. And then let's redraw our new resonance structure. And so now what we're seeing is this negative charge gets distributed right across these 2 oxygens. And sometimes you see it abbreviated like so. Let me rewrite it so you'll see this carbon, oxygen, and kind of this like dots everywhere. And sometimes they'll just like stick the charge in the middle, again showing, right, that you have resonance and this negative charge is distributed among there. And so that's, again, what makes it stable. So the fact that you have this resonance structure, so we can stabilize this negative charge all along this carboxylic acid group. All right, so now you're halfway to OCHEM, basically. So you should start to feel good. And so now looking at bases, so general properties of bases. And again, right, things taste a certain way to like give you information, right, your taste buds. So bases are often poisonous, and so any sort of alkaloid plants tend to be poisonous, and so you taste that, right, like they taste bad. They often feel slippery to the touch, like soaps, of course. They can neutralize acids. I don't know, bleach. If you ever get it in your hands, right, that also feels a little slippery. And then, of course, they also taste bad, like eating soap. Although now I think that's like what they call abuse now, child abuse. So I guess you can't wash your kid's mouth out with soap anymore. And then other bases. So we've kind of played with them, you know, over the course. So sodium hydroxide, potassium hydroxide, those are obviously used as strong bases. They can also be used in like soap manufacturing, which is always fun if we always wanted an extra project in here. Or plastic manufacturing, cotton processing. And then we have sodium bicarbonate, so that's good old baking soda. Some people drink it for health as well, and acid. It's also a source of CO2, so we've done those experiments in lab. Sodium carbonate, so this is another water softener, also used in glass and soap manufacturing. And then good old ammonia, right, our fertilizer, so that's used a lot. So mainly as fertilizer, Can't understate that enough. All right, so now we have our hydronium ion, and all we're saying, especially, right, since I wrote this carboxylic acid and I kind of had this proton just leaving, well, that's not really proper. And so all we're saying is we can't have a little proton in the water, right, so they wouldn't exist. So if I were to be more proper about things, so we could look at our carboxylic acid group again. OH, so it doesn't matter what's on there. And so then we could take some water, and we're kind of getting there, but we'll make that more clear as we finish this chapter. So water is amphoteric, if we don't remember, or we probably haven't covered that. But water can just act as an acid or a base, so meaning, right, it donates or accepts a proton. So in this case, it can come along, right, it has those lone pairs, and so it can technically pluck off that hydrogen, and so that's what really, again, drives the deprotonation. And so then we form hydronium here, and so that, again, is all that this is saying. And so we never have just H plus, but really it gets swooped up by water right away to make this hydronium. But like we'll see, right, chemists generally just write hydronium as H plus. So they're used interchangeably, right, but just know that this doesn't really exist on its own. But again, you'll see it all the time, especially in OChem, right, of just hydrogens floating around. But and not to get too detailed, but like depending on your OChem professor, some people are like very okay with just like, woo, proton transfer. Some people really want to show like water coming on, water takes it, then water gives it back. So yeah, you'll get there and kind of see it, whether they really want this water mechanism shown in great detail, the protonation, deprotonation. All right, so then we can look at our overview of our definition of acids and bases. And then in this class, we do want to start to appreciate the Lewis definition. So let's just start off. We'll go back to this overview. Let's just look at our Arrhenius theory. So this is our like simplest form and kind of the first definition of acids and bases, right, when they're trying to establish what's an acid, what's a base. And so most simply, we find, well, acids tend to produce H plus ions, right? We see that with HCl or any other, right, nitric acid, sulfuric, right? So they're always donating these ions, which again, right, we said that they're really hydronium, but moving forward. And then base, they tend to produce hydroxides. So right, anything with a hydroxide on there is pretty obvious it's a base. So sodium, potassium, calcium hydroxide as well, right? So anything that's going to dissociate and leave hydroxide ions. And then we've, again, kind of touched on these acid-base reactions and seen, okay, well, we have H plus OH. That gives us HOH, or formerly water. And so again, right, that's our neutralization reaction, where we saw an acid and a base always gives us a salt and water. And so again, right, we've seen this, maybe not so simple with HCl, but we saw it with our citric acid, or right, KPH. So we can think back to labs. And again, potassium hydrogen phthalate, not just KPH. Citric acid, just so we can, again, remind ourselves of things we've done in lab. So acid plus base, again, gives us some salt. Remember, we made like a sodium acetate salt with citric acid. And like I said, we're getting into that in the chapter. And then, of course, water. And so just a reminder as well, right, the formation of water, this is what drives the reaction forward. Since we are just forming, right, a soluble salt, so this is not going to drive our reaction forward. It's our complexation of water there. And so the problem with Arrhenius theory, and why we'll get into the next definition probably after our break, and we may know this, again, you guys have seen stuff, you're now, almost to the third quarter of Gen Chem, but it doesn't explain, so why is ammonia basic, right? So I think you guys know that from just playing around in lab. But right, there's no OH on there, so that's not obvious why it's basic. And then it also doesn't explain how our sodium carbonate or sodium oxide, right? Again, there's no OH on there, but yet they can dissolve in water and form basic solutions. All right, so even though they do not contain. And so again, we just need to figure out a better definition, and it doesn't explain why CO2 dissolves in water to form acidic solutions, right? Even though there's no hydrogen on there. And it also doesn't explain acid-base reactions outside of the aqueous solution. All right, let's take a little break for there, and then we'll pick up with our Bronsted-Lowry acid-base theory. And then I'm going to try to hand back a bunch of papers while you guys are on break. Like I said, I have a lot of papers to get back to y'all. All right. We all make it back from break? Oh, sorry. Keep doing that. So again, double check your papers and everything. Make sure that you don't have other people's stuff. So I just had another incident, right? Papers just get attached. So double check that you have your papers. And I didn't accidentally hand you somebody else's. So again, just double check your grades. Keep an eye on things. I do have some no names if you're missing. I think it's chapter 9 or 13 homework. I've been trying to do handwriting analysis, but I still can't figure out whose they are. So, all right, let's keep moving on then. And so, okay, well, how do we count for ammonia? And so now it defines our acids and bases as to kind of what happens. And so this is kind of more straightforward. And we have, so our acid is defined as our H plus ion donor. And then this is where the definition kind of changes, right? So now we don't have the base as being hydroxide defined, but rather that it accepts our proton, right? So our acid is our proton donor, our base is our proton acceptor. And then what kind of helps you with the base is that, right, usually there's some lone pair of electrons, like ammonia, so we can look at ammonia a little bit more closely. So writing out ammonia, so it has those two lone pairs. Sorry, my H's came out funny. And then again, water's amphoteric, so we have to figure out, is it an acid, is it a base? But we can see that in this case, right, ammonia is acting as my base. It has these two lone pairs. So now it can deprotonate our water. And so now we'll make, right, ammonium. So positive, right, so there's our conjugate acid, technically, since it's now our new protonated species. And then, right, water got deprotonated. And so it leaves behind, right, our conjugate base there. And then by our definition, well, now it does make, right, OH ions in solution. Our ammonia, right, makes hydroxide. And so there's our base again. And so we can see, right, how the definition is still inclusive, right? So we go back to our Arrhenius definition, like HCl. Well, it still follows under the definition of Bronsted-Lowry. So we have HCl. Again, it dissociates. And so instantaneously, the water picks up our hydrogen from HCl, again, from the dissociation, or again, really instantaneous. So picking up that proton, and again, now making our conjugate acid. So with more protons on there. And then this would be our conjugate base, since it is lost a hydrogen. Yeah.
What was the word used for water where you acid and base? It wasn't amorphous. It's something close.
Amphoteric. It should be, it's somewhere in the notes. I was trying to find it. We'll get to it. I can write it out too. Where could we write this? So I'll put H2O is amphoteric, which just means it can be an acid or a base depending on the situation. But like I said, it's somewhere in these notes later on. We'll go over that a little bit more closely. All right, so sorry, scrolling around. And so then, so we saw this, so I jumped the gun and already did it, but again, just make sure we're paying attention to our definitions. So then again, our ammonia started off as our base, those lone pairs being that big hint, right? So again, it's telling you the reactivity. So those lone pairs want to snag up some proton. We have our water then acting as our acid, right? Because it's donating a proton to our base. And then again, that forms our conjugate base, which is our proton deficient species. And then our conjugate acid, right, which is our proton plentiful species. Feeling okay about base? So our base makes our conjugate acid, right? Our acid makes our conjugate base. So just definitions. And then, I mean, this starts to tease the equilibrium that we're going to see of our acid and our kind of base species. So again, we can see that there's some sort of equilibrium. And then again, we can kind of flip this equilibrium reaction, but we'll get into it. And so then what we want to recognize are, again, our conjugate acid-base pairs. And so really what we want to look at is what makes a conjugate acid-base pair is just a difference in a proton, so either plus or minus. So that's what I was trying to show, that either we've added a proton or we've lost a proton, but it's just one proton. So it should just be one proton difference. And so looking at these, right, like ammonia and ammonium is a base acid pair. And again, they just differ by one hydrogen, so you added a hydrogen. Or we have water and hydroxide. So again, that's an acid-base pair differing by one hydrogen. But then something like that could be on an exam that's like, okay, identify the correct conjugate base pairs or which isn't, blah, blah, blah. Don't get tricked by anything like this, right? So this is not a conjugate acid-base pair, right? Because there's a difference of 2. So we skipped too many. So we want to go from hydronium to water. That would be an acid-base pair. We can go from water to hydroxide, but we can't skip like this. So this is not an appropriate pair there. All right, so again, that 2 hydrogen difference doesn't make it an appropriate pair. But again, everything else, right? So again, base, acid, acid, conjugate base, just differing in one hydrogen. And then just to kind of re-emphasize it, right? So again, a base will accept a proton, becomes your conjugate acid. Acid donates a proton, becomes your conjugate base. All right, so see if you can practice that real quick with these 2 scenarios. So again, you want to identify, so who's your acid, who's your base? Water could be either one. So start with the other species. So let's see how we're doing. In chat, you can put, who's the acid, who's the base, and conjugate base, conjugate acid. So we have our sulfuric acid, plus I'll draw out water since we'll see what water is doing. And then it makes our hydrogen sulfate complex plus hydronium. And so let's see what happens, right? So we have our water, and then it goes and it plucks off one of these hydrogens, right? So then what's water doing? Acting as an acid or base? So it's a base, right? Since it has those electrons, it wants a proton, so it's accepting a proton. And then, right, that makes sense that our sulfuric acid is our acid species, right? It's donating 2 protons. And then now we lose a proton. So this is our conjugate. Good. So conjugate base, excellent. And then what does that make our water? Excellent. So did everybody get that one? All right. So now let's see water act in the opposite sense. So now we have, right, our carbonic acid, or hydrogen carbonate, excuse me, disassociated, and plus water. Again, we'll see what it does. And then we make H2CO3, so our carbonic plus OH. And so let's see. So then that means that looks like our carbonic acid, right, is going to pluck off one of our hydrogens from our acid. And so that's how we make, right, our OH species. So then this is acting as our acid, right, because it donated. So then what's HCO3? So our base. And then what does that make this carbonic acid then? Excellent. So conjugate acid. And then, of course, this is our conjugate base there. Excellent. Questions on that one? And so then our textbook doesn't necessarily cover the last definition, but again, since we're 200 level chemistry, and I mean, eventually you'll be going on, hopefully. But with the Lewis definition, so this is, right, the most expansive and based on electron donors and acceptors. So ultimately, this is what you want to see, and you'll probably, again, go over this definition in OChem. But kind of what we see are these like Lewis pairs. And so kind of the typical Lewis pair that you have is ammonia and then like some sort of borane complex, right? So then we can see what's going on in this bond. So we have our bases or substances that donate an electron pair. And so that's why like ammonia or any sort of amine still falls under this definition. So again, a base now donates electrons. And so that's what it's doing. And then I brought up BF3, right? Because it doesn't really seem like an acid by our other definitions. But by this Lewis acid-base definition, right, this goes back to boron, how we typically see it, right? It's electron deficient, typically, since it makes 3 bonds, right, in a lot of the compounds we see, like boron trifluoride. And so that makes boron kind of upset. And so with that, again, it wants to make an octet. So it wants to accept those electrons. And so that's what makes it a Lewis acid. And I think we've looked at this type of bonding because, again, it creates this weird, unusual bond as well, which I'll redefine again so you're prepared as you move on to other courses, but this weird arrow is showing what's called a dative bond, which means that the electrons come from one atom, right? So basically 2 electrons coming from one atom, as opposed to, again, right, our normal bond where each atom contributes 1 electron. So again, that's our dative bond. So again, we're seeing that the amine is acting as a base. Our boron is accepting it, so it's our acid. And then I just want to bring it up as well because this whole concept of Lewis pairs is used in like research then to make these frustrated Lewis pairs where basically you put things that are an acid and a base like really close proximity and then try to get them to do kind of cool stuff. And so you can kind of see the introduction to it on Wikipedia, right, where these frustrated Lewis pairs, maybe the idea is that you get them to like do something cool with small molecules, and so that's why some of them can do like some sort of hydrogenation. But anyways, we don't want to go down that rabbit hole. I'm just showing that there's like a whole field of chemistry related to these Lewis definitions of acids and bases. All right, did we finish? Should we finish that page? All right, so now we're getting into, at least slowly, the equilibrium part. But let's establish a few things. So we have to recall that there's 2 different types of acids. And right, it has nothing to do with like how much it's going to hurt when it touches your skin or anything. That's not what the definition is about. So a strong acid or base completely disassociates. And I probably misspelled disassociates. And so that's what it means by this statement. So a strong acid, again, complete or near complete ionization. So meaning HCl, you put it in water and it completely disassociates, right? And I think I've mentioned this before, but we could have, let's just say, 1 molar of HCl, and then we know it's going to make 1 molar of ions, right? And then later we could plug this in for the pH, which we'll refresh in this chapter. It makes 1 mole of chloride ions. And so the problem with the weak acid, oh, and that's right, we had touched on it to do your distillation lab. That's why I remember talking about it. And so a weak acid, though, only has some small percentage, right, that's partially ionized. And so that's why there's the equilibrium. And, you know, if you recall from your calculations, so that's where the Ka and all that comes into play. And then so same sort of definition, right, for the strong base and weak base. So again, your strong base completely disassociates. And so this tends to be like your ionic base compounds, we'll just say. And so what I mean by that, so KOH, right, NaOH, calcium hydroxide. So the only caveat with like calcium hydroxide is, remember, it makes like 2 equivalents of hydroxide ions. But same thing, right, complete disassociation. So that means 1 molar solution of KOH, right, will make 1 mole of hydroxide ions. But with our weak base, only, again, we're looking at a small percentage, so we have the equilibrium value. And then, so there are a few just general trends. And, okay, so this is one thing. So it says the stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. And so the way I would think about it is, well, let's think about HCl, right? And if we think about that, the problem with HCl is, so this would be your conjugate base, technically, right? Our chloride. But the thing is our chloride ion is basically such a poor base that it's never going to accept this proton, right? So that's what this is saying. But if we look at a weak or a weak acid, so this was our strong case. And okay, so again, just to recap, right, we had a strong acid, equilibrium was all the way to the right, but then that means our conjugate base will never accept a proton. But then if we look at, so HF, right, does disassociate by some equilibrium, right? So there's not a complete disassociation, but because HF is a little weaker, now our conjugate base, right, can accept our proton again, or really what happens is, right, we could put it in water basically, and then it would reform HF and technically leave us with hydroxide in this case. So again, right, all we're saying is kind of the opposite, right? So if we have a strong acid, then our conjugate base cannot reform. But in this case, we have our weak acid, so then, right, our base can accept a proton. And this will become more clear as we play with the Kas and the Kbs and look at other charts. This is just a general statement. So higher oxidation number, the stronger the oxy acid. So just looking at that, sulfuric is a stronger acid than sulfurous. And again, we'll look at that with kind of the Kas. So same thing, you have nitric is stronger than nitrous. And so nitrous is a weak acid, right? And again, it has some sort of Ka, while you guys know that nitric is a strong. So same thing, right? This is a strong acid. This has some sort of equilibrium. And then we'll point out a trend here, but let's kind of look at what it's saying. So we have a cation is a stronger acid than a neutral molecule. And so now we start to get into this other trend, right, that cations, if they're anything, they're going to be acidic, right? And then, or they could be neutral. And then it says neutral molecule, stronger acid than an anion. So that means, right, our anions, if they're anything, tend to be basic, right? But again, we'll kind of keep looking at these trends. And so I knew I forgot to print something out. So I'll print this out for Thursday. I'll try to get it in color too. So this is your cheat sheet for the chapter. And so what's kind of nice is up here on our acid column. So right, this is increasing acid strength. And then up here, so these are your strong acids, right? And then what this is saying, so notice this is the conjugate base on the other side. And then it makes a statement, so do not undergo base ionization in water. So what this is saying is these are not going to reform the acid, right? They're not going to reform this acid in water. So you're never going to have a chloride ion, again, reacting with water to give you HCl, right? That's never going to happen. Now, that being said, so let's look at something else. And this will be a good safety tip. So now looking at HF, so now these can, right, go back and forth. So once we're past this line here, and again, increasing base strength. And so again, this means if we're using some salt, or even if we're producing something, so let's say we've made, I don't know, sodium fluoride as a byproduct of some reaction. So what's dangerous about sodium fluoride then is, again, this fluoride can go ahead and react with water, and like I've shown earlier, can reform HF. And so this is, right, a safety hazard. And so you'd want to be neutralizing your waste as it came out to, again, prevent the formation of HF there. So you want to neutralize any potential HF. And so again, that's a big safety concern when you're trying to think about your reaction. And so anytime you're working with like fluoride salts or anything, right, you have to think about your byproduct. Am I creating fluoride salts that I then need to neutralize? And then this is a nice chart. So you have all your acid-base pairs, right? They're always just off by one hydrogen across. So that's nice. So this helps you, right? Okay, so nitrous, you can tell that that's a weak acid. So again, all these are weak. And then until we get down here, where we have, again, do not undergo acid ionization in water there. So meaning, right, they're not going to be just spontaneously losing a hydrogen, right? Like ammonia is not going to become NH2, right? That's not, does not work there. All right, so then, like we said, our strong acids, and now starting to put the Ka into play slowly. So Ka, again, if we draw out, I was hoping, this is what I was looking for. So looking at our Ka expression, and so again, I'll write it over here. So Ka, so that is acid. So conjugate base times our H plus concentration over however much is still together. So that's our Ka expression. So then, okay, we're saying where our Ka is much greater than 1, again, because this is being consumed and it's all of our products. So again, 100% ionization of acid molecules occurs in water. And then these are our 6 strong acids. So I would, write them, highlight them. Again, this chart will probably help you, so I'll have that printed for Thursday. So you have your strong acids. And again, we're still kind of teasing this, but our weak acids, so then our Ka is less than 1, so only a fraction of their of the acid, right, ionized. And so they do not donate much of their hydrogens to our water here. And so, again, just a representation. So just paying attention to the pictures where the HCl, right, there's none of it associated. And it's all hydroniums. Versus the weak acid, right, where there's still a few HFs still associated. And then, so acetic acid, we see it often as a weak acid that we work with. But then there could be, right, carbonic or formate, or there's quite a few. And so mainly we've been looking at our Ka expression. So there's a few things to look here. And so, of course, the farther the equilibrium position lies towards the product, the stronger the acid or the base. So there's our hypochlorous acid. So that's 10 to the minus 2. So that's still fairly strong versus our hydrogen cyanide, which is 4.9 times 10 to the negative 10. So that's a lot weaker, right? So we can tell that this is a stronger acid. All right, so then this brings us back to our Ka, like we saw. And so again, just writing out our expression. So our acid plus water gives us hydronium plus our conjugate base. And then, right, our water is a liquid, so it's not included in our equilibrium expression, right? Just following the rules from what we've seen before. Again, the larger the Ka, the stronger the acid. So this is probably a useful chart. I think I stole it from your book. And so again, you have your Kas, and then we might as well look into this pKa and how to calculate it. And so this pKa is just equal to the negative log of our Ka value there. And so we can test that out. I'm just doing the first one. So right, negative log of 1.1 times 10 to the negative 2. And so that gives us, right, 1.96 roughly. So that gives us our pKa. And then what's kind of confusing is, right, the lower the pKa value, the stronger the acid, right? And as your pKa value increases, like to 9 or so, then you actually have a weaker acid. So kind of confusing. But at least you want to start familiarizing yourself with this concept of pKa. Organic chemists tend to love talking about everything in pKa's and pKa values. So that's the terminology that you'll see much more in OChem. So here's the amphoteric definition that we were looking for earlier. But something else that we want to point out with this is the auto-ionization of water, which is pretty cool. But it gets into like why our pH scale is the way it is. And so looking at water, and so again, there are other substances that are amphoteric, like aluminum and such, but we'll get to aluminum later. And so again, it's amphoteric, which just means that it can act as an acid or a base, right, depending on the situations. But then that must also mean that there has to be a few ions present. And so this is also what they found, like way back in the day, right, when they're trying to figure out pH and everything and how many ions. And so they were just measuring, right, the concentration of kind of H plus ions in water. And so if we look at this concept and how it can work, so we're saying that there's a small amount of water, right, that is deprotonated. So meaning sometimes when two waters see each other, so one of them can act as the base, so then it deprotonates one water to give us hydroxide formally and hydronium. Okay, and so again, right, this is a minor amount, but what was found is, so they found that they are equal in water, at least, right, at 25 degrees Celsius, and they found that it was 1 times 10 to the negative 7 molarity of each. So that was pretty cool. And then this leads us into other kind of constants, and again, you're kind of seeing where our pH scale is coming from. And so then it says that the product of hydronium and hydroxide concentrations is always the same at room temperature. And so that's 1 times 10 to the negative 14. And so we formally have this. So our hydronium times hydroxide equals Kw, which, like we just established at 25 degrees Celsius, is 1 times 10 to the negative 14, right? Just plugging in these values. And so we're not really going to deviate, right, from the 25 degrees Celsius either. So for our purposes, right, just assume that this is the concentration at this temperature. And then what's kind of useful, though, is we'll see how we can use this later to solve. So, right, if we know our hydroxide concentration, then we can figure out our hydronium. So they just have to equal to 10 to the negative 14. And of course, as one increases, the other decreases. So they're inversely proportional, which you've probably gotten a sense of from our scale. And so again, just kind of more definitions for now. So we're establishing that aqueous solutions have some amount of hydronium and hydroxide. So if something is neutral, then it has equal hydronium and hydroxide. So that's going to be 1 times 10 to the negative 7, again for our conditions and assumptions. And then acidic solutions will have a larger hydronium population than hydroxide. So anything larger than 1 times 10 to the negative 7. And then hydroxide will be less than that. And then basic solutions will be the opposite. So larger hydroxide than hydronium value. All right, so see if you can do it this way, and then we'll kind of look at pH, which probably make these calculations easier. But so the Kw is just our water product constant. So 1 times 10 to the negative 14 if you needed it to calculate. So yeah, let's see how we're doing. And so what do we think for A? So is it acidic, basic, or neutral? And then, yeah, somebody did ask for the Kw, so we just have to remember what was that definition. So our concentrations of each is equal to 1 times 10 to the negative 14. So looking at A, so before you start punching away, so what do we think? Acidic, basic, neutral? Yep, so acidic, right? Since we're looking at hydronium, it has more than 1 times 10 to the negative 7 molarity. So acidic, good. And then we can plug in and calculate our hydroxide concentration. So then 1 times 10 to the negative 14 divided by our hydronium concentration of 7.5 times 10 to the negative 5th. And so we should get a hydroxide concentration of 1.33 times 10 to the negative 10. And again, right, that's showing you that it's a smaller concentration. So they should be complementary. And so what about B? Acidic, basic, neutral? But yeah, if it's neutral, we want it to be like right on neutral. Otherwise, classified as acidic or basic. So what is it more towards? So basic, right? So now we have a smaller concentration than 1 times 10 to the negative 7 molarity. So it'd be basic. And again, we can calculate our hydroxide concentration. oops, sorry. So about 6.67 times 10 to the negative 7. So again, that's greater than our 10 to the negative 7 kind of middle point. So basic. And then our last one, so is it acidic, basic, neutral? So neutral, and then hopefully we don't have to do math, right? But we should just know our mental math. So 1 times 10 to the negative 7 for our hydroxide concentration. And then personally, I don't really like doing acidic, basic, neutral like this. And so we can look at how to calculate our pH, which we might be more familiar with. So just our negative log of our hydronium concentration. And so for this chapter, again, just make sure you have your calculator and you're practicing along. It's usually not too difficult, but you just want to make sure, like I said, your calculator's in the correct base. Oh, I'm throwing my pen. So sometimes, especially if you have, like, I want to say a financial calculator, sometimes they'll be in the wrong base or something weird. So that's why I'm saying just make sure that you're plugging along and checking that you're getting the same answer, right? Your calculator is spitting out the correct stuff. So let's just double check it for A, right? So we can plug in 7.5 times 10 to the negative 5th here. And we get about 4. And so you can see that you can roughly guesstimate your pH, right, by this exponent. So it was about negative 5, so that's kind of what I was expecting. So closer to 4. And then same thing, let's plug in this next one. So negative log of 1.5 times 10 to the negative 9th. So right close to 8 there, which is what I expected from our negative 9. So again, showing us that it's on the basic side, like you all predicted. And again, it's just easier to compare. So greater than 7 is basic, less than 7 is acidic, and then at 7 is neutral. This just gives you kind of an idea, right, of representative substances. Obviously, your gastric juices are at a pretty low pH, right, to help dissolve everything. But that's also why, well, if you were bulimic or anytime if you were to throw up, right, you want to rinse your mouth out. But obviously, people with bulimia have teeth issues. Although now with Ozempic, I guess bulimia is not a thing. No, bad joke. But we have limes and lemons. So of course, right, those could erode your teeth enamel. So now I'm talking about teeth, being paranoid about teeth. And that's why they say, like, right, like maybe don't brush your teeth right after drinking orange juice. Like give yourself some time to drink away the acidity so you don't rub off all your enamel with the acid you just consumed. So that's the other issue, right? Like wines as well can be kind of damaging to the teeth enamel. And then we can see, right, most fruits are kind of acidic. And then rainwater, we'll see how this goes. I think we're collecting a fresh sample from one of our labs. So it could be, somewhat acidic from all the pollutants. So again, you'll see that. Human blood is obviously kept as a tight buffer. The biology-minded people in here, I'm sure, can tell us more about that. Egg whites, same thing, right? Those are kept at a tighter buffer. And then milk of magnesia, maybe some people consume this for like an upset stomach, but that's another standard like household base of around 10. And then you have ammonia, which again is pretty basic. And then obviously your sodium hydroxide solution is pH 14 there. Okay, so we'll try to find a good wrapping point today. Well, I guess we'll just end on these. So calculate the pH really quickly. see if you can do it. We have this hydroxide one. All right, so in the interest of time, I'll just work through them. So again, this should be easy enough to plug in for A, right? We're already given hydronium. So 1.8 times 10 to the negative fourth. So I'm expecting it close to about 4. So 3.74 for our pH. Somehow threw my pen somewhere last minute. So 3.74. And then this one was a little tricky, right? So kind of based off of what we know, kind of maybe what you had to do was go back to this formula, right? So then we can do our KW, so 1 times 10 to the negative 14, divided by our OH concentration. So then we get that, right, for our hydronium. So 7.69 times 10 to the negative 13. And then we can plug that in. Or we're about to leave off on the next thing, which will make it easier. And some people may already know this because some of this is basic. So then we get 12.11 for our pH. Or we're about to tease POH. So POH is just a negative log of OH. So really what we could have done, and this is why I like pH, the pH chapter, because there's lots of ways to get to the same answers. So we can plug in our hydroxide. So that's our POH, right? And then we could take 14 minus this, and we would have gotten our same answer as well of 12 for the pH. So we'll leave off on there. So we'll pick back up with this POH in case you didn't quite follow. And then we'll get to here, but like I said, I don't want to go too fast, even though you can probably see it. But this is another relationship that's related to our KW and makes things quite nice for us. All right, so we'll pick up there. And then we will at least kind of maybe touch on titrations and buffers just a tiny bit, although we'll probably end up saving a lot of the equilibrium stuff for kind of next quarter. So we're kind of doing more acids and bases definition on this chapter, but like I said, right, don't trash your equilibrium memory because we're going to need it next quarter. Potentially, but the problem is the strips are not very accurate. So then you could use like a pH probe, but yeah, that's kind of the idea because I think the KW constant is not like perfectly 1 times 10 to the negative 14 at different temperatures. I forget what it is, but yeah, that's kind of the idea. It's pretty small, yeah.
Got a question based on the calculations. So I don't know that is the